Namaste students, welcome back to Rama Teaches You. Today we are going to do a brand new section, the E section. Okay, so in E, the topic that we are going to deal with is nuclear and quantum physics. Okay, so nuclear and quantum physics is divided into a lot of chapters. The first chapter that we are going to deal with is known as the structure of atom. So, introduction. The scope of theme E ranges from the smallest fundamental nuclear particles to the largest structures visible in the night sky. Scientists have been fascinated by these largest and smallest objects in the universe throughout history. All three of the overarching concept of physics merge in theme E. Nuclear material is in the grip of three interactions: strong electromagnetic and weak. These give rise to forces that act between fundamental particles. When energy is sufficient to overcome the attractive forces, then nuclear changes can occur. Okay, nuclear changes will occur if we are able to provide more energy or more force than the force that or the energy that exists between the fundamental particles. Now, throughout the century, scientists have observed matter on Earth and the night sky above with greater and greater magnification. For, for falsification of theories and subsequent paradigm shift have been driven by the discoveries about atoms and the universe. The Greek philosopher Leucippus and Democritus in the 5th century BCE were the first atomists to suggest that atoms were indivisible. The idea remained in scientific thought up to the 19th century. At the turn of the 20th century, argument about the nature of matter still persisted. Ernest Mach died in 1916 without acknowledging the existence of modern atoms. Boltzmann had already embraced the idea and had argued that the point with him in 1897. But despite Mach's reluctance, physics was about to change forever. Topic A5 and E1 with Einstein's application of mechanics to the Brownian motion in 1905. The global impact of nuclear physics was immense and continuous to that day. New scores of energy have been discovered, and these can be used for goods or for ill. Now, basically, like we have the atomic energy. Atomic energy is being used for good every single day by using in nuclear power plants or for X-rays and all the other stuff. Okay, whereas it can be used for evil also, like the atomic bomb. Okay, new methods for medical diagnosis and treatment for illness have been developed involving nuclear science. Radioactive tracers give us insight into the world of the invisible. The pursuit of science has ethical consequences. Scientists must assess the risk of their work, weighing these risks against benefits. They should aim to do no harm. Okay. So it's a good thing that they're saying. Basically, if some of you actually go into research, you have to decide the research study that you're doing has to benefit humanity overall. Okay, anything can be used for good as well as for evil, but if your work is going to benefit the greatest humanity, then it is your responsibility to do that work. Okay, our starting point for the theme is the atoms are composed of nucleus and electrons. The nucleus consists of nucleons, the protons and the neutrons. Protons have positive charge, and neutrons, as the name suggests, has no charge. Outside the nucleus are electrons. The charge of one proton and the charge of one electron have the same magnitude but opposite sign. Do you know? So your knowledge of the electric forces described in theme D will be important. So we know that what is an electrostatic force? An electrostatic force is a force that exists between two charged particles. It can be attractive force in the case of two unlike charges, like for a positive and a negative and a negative and a positive, or it could be a repulsive force between two like charges, like a positive and a positive and a negative and a negative. And lucky for us, the nucleus has protons, which is positive. whereas the electrons are made up of negative charge. So there is an electrostatic attractive force that exists between the two charges. Okay, earlier theories of the simplest atoms were based firmly on classical physics. Your knowledge of the mechanics of theme A will be important too. Later theories of the atoms involve wave mechanics, which relies heavily on the concepts from theme C. Now, in theme C, we learned something known as what? Wave equations, oscillations, right? We understood the various like standing waves and all the other stuff. Now, here, what is going to happen is we are going to consider the electron, which is supposed to be a particle, a matter. We are going to consider it to be a wave. Okay, and that is the basis for all of quantum mechanics. Okay, the Schrodinger wave equation. Quantum mechanics basically starts from the assumption that matter, that is electron, a subatomic particle, even though it has mass, it could, in theory and principle, behave as if it were a wave. Okay, so the dual nature of matter is what gives rise to the quantum mechanical model of an atom, or simply quantum mechanics. Okay, now we are going to start the first chapter. The first chapter is going to be E1, structure of an atom. Okay, what is the current understanding of nature of atoms? In what ways are previous models of atoms still valid despite recent advances in the understanding? What is the role of evidence in the development of models of an atom? Okay, we are going to understand whole of this. Our understanding of atoms and nuclear structure has come a long way since the work of J.J. Thomson and his discovery of the electron 130 years ago. We now understand that the atom consists of a nucleus at the center and a cloud of electrons. Originally, one of the two ways or types of nucleus were thought to exist. These were the protons and the neutrons. Physics now has a standard model that describes the compensation of protons, neutrons, and other nuclear particles using more fundamental entities. Now, we have already discussed about protons and neutrons, but what are these protons and neutrons made up of? That's what we are going to discuss in this chapter. This model was developed during the second half of the 20th century by many physicists, building on the data from the high energy colliders such as the CERN and the Brookhaven colliders. Now, basically, what is a collider? Okay, what is a particle accelerator? So basically, these are these giant miraculous. Okay, their work. If you see in front of you, the size of these particle accelerators will make you so amazed. Now, look at this. What is going to happen? You know that a charged particle can be accelerated through an electric and magnetic field, right? We know this. In the previous section, we studied this motion of a charged particle under the influence of an electric and magnetic field, right? Now, what is one second? What does the collider actually do? It accelerates the charged particle to such high speeds, and then simply, as the name suggests, it makes the two particles collide. Now, it does not just simply collide one particle each, okay, from two different directions. It collides thousands of particles, okay, hundreds of thousands of particles collided like this, okay. And when the collision occurs, the result of this collision gives the scientists a small insight into what the subatomic particles could be made of. Understood? So it's like basically if you want to see what is inside a rock, what do? You break the rock, right? How do you break the rock? You break the rock by smashing it with some other thing like a hammer, yeah, or simply you throw it into another rock and that rock actually breaks. So basically you're crushing the rock by smashing. Similarly, we are crushing the atoms by crashing. We are crashing the subatomic particles by basically colliding them with each other so that we can see what is inside those particles. Okay. Like a reactor. Exactly. Not a nuclear reactor per se, because a nuclear reactor does not work on the same principle as that of a CERN super collider. A nuclear reactor works on the principles of basically decay of atoms. Okay, a big atom like uranium eventually decays into two different atoms, resulting in a large amount of energy release, which can be used to heat up water that will eventually rotate a turbine. Okay, that is something different. Now, the result and methods of early Greek thinkers are in strong contrast to those of the present day nuclear scientists. What part what part does evidence play in modern science? Okay, this is an essential question for you throughout this course. In theme E, you focus on how scientific evidence leads to models of the atom and the nucleus. Atoms are invisible to the naked eye. We need powerful instruments to image the electron distribution that exists outside the nucleus. Accelerators use immense energies to help us infer the properties of the nucleus and the forces that act within it. Okay, early philosophical world views such of as these of ancient Greeks came in various perspectives. These sometimes focused on the simplest possible explanation. Some Greek thinkers, for example, described matter as made up of elements like earth, fire, water, air, etc. Because those were the fundamental particles that they were able to observe in their surrounding. The earth, the land that was beneath their feet was earth. The water that they drank, the air that they breathed, the fire that they used to keep themselves warm, all of these, and ether. There was one more thing called ether. Okay, and that's what they call the life energy. So these are the five things that they believed all matter was made up of. Okay, next. In 1989, the company IBM demonstrated new technologies that enabled them to place individual atoms for the first time. This picture shows 35 xenon atoms, spelling the name of the company, IBM. This is made up of 35 xenon atoms. This is actually pretty cool. Okay, next. As ideas, these ideas are a long way from the present list of stable and unstable elements that we will meet in topic E3. We should not dismiss earlier ideas simply because they are old. Okay, so the thing is, why do we learn something that is wrong? Okay, we know the J.J. Thomson model is wrong. We know the Rutherford's model is wrong. We know the Bohr's model is wrong. But why do we learn these things? We learn them so that we could understand and basically understand the process and the efforts and the evidence based research. Okay, whatever evidence is in front of you, you have to know how to use that evidence and make up a particular model. And that is not just the case for chemistry also. Anything that is in front of you, there will be some amount of evidence, some amount of resources, some amount of information that you have. With this information, you have to come into a certain conclusion. You have to come to conclusion about what this evidence is actually showing you. Okay, and that is known as the scientific method. And this can be applied not just in science, the field of science. You can apply it anywhere. Anywhere in your daily life, you can apply the scientific method. Okay, the evidence that is in front of you, you have to come into a conclusion by using that evidence. Okay, now the scientific method, see, that's what I was talking about. The scientific method changes with time. The accepted views of both cosmology and nuclear science have altered throughout the past 150 years. Now, something that we can learn from the scientific community is that when you're wrong, it's not a bad thing. It's basically giving you the opportunity to make your understanding deeper. There is no ego in, I know science, there are a lot, there is some amount of ego, but science as a whole, I believe that it is the great equalizer, because every single time a new theory comes up, there is a possibility that that could be disproven in a couple of years or in a couple of decades, and that is absolutely normal. Okay, we have come a long way to understand the various different models of an atom. And in a couple of decades, maybe we could actually have a model that works better than the quantum mechanical model. So, what will we do? We will basically uh, go from the quantum mechanical model and accept the new model, because that is what science teaches us. Okay, you should always move forward. You will always have some amount of challenges. You will try to face some of these challenges on your own, but after a while, then when some new challenge comes, you will at least know that the previous, you will know, you will have the experience of actually combating the previous challenges. Now see, if you know the JJ Thompson's model, okay, the plum pudding model, now in the future no one would actually try the plum pudding model again, right? Because that has already been disproven. Okay, so you need to understand the theories that have been wrong, so that you could end up making new theories in the future. Okay, let's move on. That's a lot. It was basically something that I always think. Okay, this chapter, because we go through so many theories, and every single time when I teach the students, they say, what is the point of learning something that is not true? Okay, there is a point. Everything has a point. Okay, sometimes scientists resisted changes for the reason that were not scientific but were based on dogma and bias. Modern research into the nucleus is carried out by large teams of scientists. Okay, a lot of people are working on this project, usually drawn from all parts of the world. Their work demands large, powerful, and expensive machines that collect large amount of data. The analysis of these data then requires much powerful computers, and the results of the analysis, usually statistical in nature, allow scientists to infer from the presence of fundamental particles. Okay, how these particles behave, do these particles actually exist? All of this stuff is inferred from the scientific data, the basically the statistical data that is generated by the computers from all these experiments. Now these conclusions are submitted to the critical peer review before being accepted into mainstream scientific understanding. Now there is one more thing that you have to understand. Just because some person says that he has discovered something new, it doesn't mean that the whole scientific community have to accept it blindly. That is something that never happens in science. Okay, the first thing that you do, they say, is once when someone actually brings forward a new theory, you know what the first response is? You're probably wrong. Okay, and then there are various tests that take place when you have these theories put forward in front of you, and when these theories and these experiments are checked, okay, if the results are as described by the theory, then and only then that theory is accepted as a scientific evidence. Okay, now all of this, the quantum mechanical model and all these theories have actually gone through these critical peer reviews. Okay, now let's see what all we are going to learn here. Now the Geiger Martin Rutherford experiment and the discovery of the nucleus, the nuclear notation, emission and absorption spectra and how they provide evidence for the discrete atomic levels, photons and how they are released during an atomic transition, the relationship between difference in the energy levels and photon frequency, the emission and absorption of photons during atomic transitions, the relationship between the nuclear radius and the number of nucleons, deviation from Rutherford's scattering at high energies, the distance of closest approach in scattering experiment, the Bohr's model of hydrogen, quantized energy, quantized angular momentum, and orbits in Bohr's model. I know this is a UK based curriculum, but if you were to look at by from the Indian NCERT perspective, you are basically going to cover structure of atom. It's a chemistry chapter. Okay, then you're gonna learn about, I guess, photons, right? I think you will learn about the photovoltaic effect, the dual nature of matter and radiation. That's a physics chapter. Okay, similarly, we are going to learn about the structure of an atom. There's a physics chapter also. Okay, and the nucleus. That's also a physics chapter. Okay, it comes in the modern physics. So basically, this one single chapter has a culmination of both 11th and 12th class topics. It's pretty good though. Okay, let's see. Deductive logic versus experimental evidence. Now, It is easy to dismiss the early ideas of elements being earth, air, fire, and water. These ideas explain why rain falls so it could reach its natural place in the river and seas, and why a stone would fall and sink because its natural place was earth. Fire, on the other hand, rose up. Burning wood released fire and left ashes behind. Wood must therefore be made of elements of earth and fire. So, Akshay, what they're trying to say here is the see, it's like this. The theories become more and more complex when the person who is asking the question becomes more and more smarter and curious. Okay, at that point of time, see, whenever a student learns something new, some people say that you should always try to ask as many questions as possible. Okay, but the student doesn't know what questions to ask because everything is new to him. Okay, so basically, the student is only going to ask those questions that he knows. Okay, there are, see, basically it's like this. Questions, you can only ask those questions of which you have some idea. Okay, you cannot ask questions about something that you are not even aware of. Okay, like basically in the 1800s, if you ask someone about what a computer is, he would not be able to answer that to you. Even the smartest physicists, smartest mathematicians, if you ask them simple stuff like what is Wi-Fi, what is radio waves, and all of the other stuff, people would not be able to answer you. Okay, because though these are the questions that have never been that have not even entered the imagination of these people. Okay, so basically in the olden days, the questions that the people had: why does the stone fall down, why does the wood turn into ash and fire, all this stuff was basically the reason why we had the five elements to begin with: the earth, fire, air, water, and ether. Okay, today the purpose of science remains the same: to provide explanation of the world. However, the tests of knowledge has changed. The ancient Greeks valued deductive logic. Modern scientists value experimental evidence. Okay, so deductive reasoning and experimental evidence are two different things. Okay, the deductive reasoning basically tells you how to see, it gives you a tool to deduce a certain problem, but experimental evidence actually checks for the viability or the credibility of the theory that is being put forward. Okay, that's why we have two different types of physics. You have the applied physics. Okay, you have the experimental physicist and a theoretical physicist. So the job of a theoretical physicist is to come up with new theories to explain the various problems that are taking place in science, okay, in the world of physics. But an experimental physicist's job is to create experiments that would allow the science to actually test these theories. Okay, that is what they mean by experimentation. Experimental evidence is actually very important to analyze the various theories that are taking place in physics. Okay, how can we determine the relative merits of these ways of justifying knowledge? Okay, introduction. Now, the beginning. In 1858, the German physicist Julius Plucker found that electric discharge through a low power gas caused a fluorescent glow on the walls of the glass container that held the gas. Okay, we are going to talk about the cathode rays. Okay, you must have already learned about the experiment of cathode rays, right? There is a tube. If not, I'll show you an explanation. Let's actually watch the video first. So, this is an old cathode ray experiment that I found on YouTube. Okay, credit where credit is due, but this explains a lot of how a cathode ray actually works. Okay, okay, so you are having a cathode and an anode. Okay, there is air, there is a gas at very low pressure between the cathode and an anode. Okay, so there is virtually nothing in between them, and you are applying a very high voltage between the cathode and the anode. Okay, so
Yeah.
there is, do you see that white milky or the chalk like powder in the center? That is a fluorescent powder. Okay, the fluorescent powder actually allows us to see the cathode rays. Okay, now what we are going to do is we are going to apply a high voltage electricity, high voltage electric field across the two cathode and the anode. Okay, and when that happens, a ray basically starts to originate from the cathode and it moves straight towards the anode, and that ray can be actually seen through this powder by using the fluorescent effect. Okay, now let's see the experiment.
On the screen, right? And as we turn on the screen,
Can you see the green
you
light?
notice that the ions are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray, this stream of electrons illuminated. We can use a
So now we know that while doing this experiment for the first time, they did not know whether this was a cathode ray or this was made up of electrons. They just observed that there was something that was moving from the cathode, that is the negative terminal of the battery, to the anode, that is the wait. Yeah, the positive terminal of the battery was the anode. Yes. Okay. So when they observed this, okay, they saw that there was a fluorescent effect. Something was moving across this low pressured gas, and it was magnificent. Okay. Let's see. Now
Is
we,
it
yeah, tell me.
as well that as it goes?
What?
Is it like electrons are like expanding as it goes from the cathode towards the anode as well?
They're not expanding, Akshay. They're not expanding. It's just like,
Yes.
see, have you ever seen an infrared camera?
Yeah.
An infrared camera's job is to actually see the infrared light, right? The heat that is coming out. Can our eyes see the infrared rays?
No.
No, they cannot see the infrared rays. So basically, what is happening here is that the fluorescent, the powder, is allowing us to view the electrons that are passing through the gas. That's it. They're not expanding. They're just going from one place to another. That's it. Okay, it's just a straight beam of electrons, and that straight beam of electrons, when they pass through this fluorescent powder, you are able to see a green light that is going from the cathode to the anode, or the left to the right. Okay, that's it. Now,
Okay.
what is the electron's charge?
1 point.
No. It's a negative charge, right? Yeah, I know. It's 1.6 into 10 minus 19 coulombs, but it's a negative charge. Okay, so a negative charge would get attracted by a positive plate, a positive charge, right? So if you place an electric field, here, the path of the cathode rays or the electrons would actually deviate. Okay, now we are going to see this person is going to actually show us how the path of the electron deviates. Okay, let's see.
To show the deflection of that stream.
Now we know that a charged particle can be deflected via an electric field as well as a magnetic field, right?
Yeah.
So this person has in his hand a magnet. Okay, and when he's bringing the magnet close to the cathode ray experiment, the tube, he is able to observe that the magnet is somehow basically deviating the path of the cathode ray. Can you see that? See.
Here we can see the electrons being deflected from the magnet. The cathode ray moves upward. If we reverse the magnet, we would predict that the beam would be deflected in the opposite direction.
Exactly.
And
See.
observe that the beam is deflected downward.
Awesome, right?
Yeah. It's to show that negative, the deflection was like the positive charge of the magnet, the negative, and then the charge of the good.
Exactly.
Yes.
That is absolutely correct. Okay, just hold on 1 second. I'm going back to the original screen. So He was able to make the glowing area move using an electromagnet. We saw that, right? Movement
Yeah.
of the movement of the cathode rays via an electromagnet. By 1869, John uh, Hit, Hittorf, one of Klucker's co-workers, had identified cathode rays. These were produced when electric charge flowed through a low pressure gas. The gas inside the chamber has to be a low pressure gas. Okay, 8 years later, Joseph J. Thomson, a British scientist, found that these cathode rays were deflected by both the electric and magnetic field and must be charged. So basically, J.J. Thomson knew that charged particle can be deflected by an electric and magnetic field. Now, this cathode ray was doing the same thing. The cathode ray was trying to deflect itself when it came across in contact with the electric and magnetic field. So, what ended up happening? Okay, he basically realized that cathode rays are charged particles, and now he also understood that as the deflection, he studied the deflection and basically came to a conclusion that cathode rays were made up of negatively charged particles, and the name that he gave to the negatively charged particles was that of the electron. Okay, Thomson eventually concluded that cathode rays were beams of negatively charged particles coming from atoms. Atoms have no overall charge, so this meant that some other part of the atom must be positive. So basically, as the cathode rays move from one end to the other inside the experiment, you are basically having a positive charge on one side and the negative charge on the other side. Figure 2 shows the model that Thomson suggested. Okay, Thomson's model is called the famous plum pudding model because he believed that the electrons were tiny raisin like structures that were stuck onto the surface of the atom. He basically concluded that there is a sphere, there is a positively charged sphere, and in that positively charged sphere, electrons are embedded as the raisins and nuts are embedded inside a plum cake, right? So basically, on top. Now, it is called the plum pudding model or the current bun model of the atom. The electrons were thought to be buried in a diffused cloud of positive charge. So basically, he believed that since there was no he was not able to identify the positive charge. Okay, he was only able to identify the negative charge. So what did he do? He said that there is a positive cloud, that there is a positive cloud and the negative electrons are just basically stuck onto that positive cloud. Okay, the positive sphere. Okay, Thomson's model was the first suggestion that atoms had an internal structure. Okay, till then, a lot of people believe that atoms, according to Dalton's atomic theory, indivisible particles, right? Dalton's atomic theory basically says that atoms are indivisible particles. Now we have completely destroyed the first postulate of atoms, given by Dalton. They are divisible. Atoms can be divided into subatomic particles, namely electrons, protons, and neutrons. And J.J. Thomson was given the credit for the discovery of the electrons. Okay, J.J. Thomson's model was the first suggestion that atoms had an internal structure. He had shown that objects smaller than an atom make up most elementary building blocks of matter. His research promoted work by others. Since then, the attempts to discover these building blocks at at ever decreasing scales have been an important part of physics. Okay, now Rutherford and Bohr's model of an atom are described in this topic. Scientists use models to describe and or explain things because a full explanation or description can be too complicated. The topic of atomic structures would easily fill the entire book and even then be incomplete and approximate. So that is why these people create models so that the common person can understand and visualize what is going inside their head. Okay, it can be tempting to dismiss a model as being wrong or simplistic. The value of a model is whether it provides a useful way of thinking about a subject. So, what did J.J. Thomson have? J.J. Thomson only knew the existence of a negatively charged particle. He had never seen the positively charged particle. So what did he know? He knew that negatively charged electrons existed, and because there is a negative charge, there has to be a positive charge, because atom as a whole is neutral. And since he was not able to see or visualize the positive charge, he concluded that the whole atom is made up of a positively charged cloud with the negatively charged electrons embedded in them, and that is what we call the model. Okay, it is a visual representation of all the theories and all the calculations that J.J. Thomson must have made while making this model. Okay, now the ancient Greeks model of an atom as an indivisible blob works well when considering a particle of gas bouncing off a wall. See topic B3. When he's basically talking about the kinetic theory of gases, where basically we consider the gaseous molecules to be perfect little spheres that can elastically collide with each other. You remember Boyle's law, Charles' law, Avogadro's law, and all of that. Yeah, okay. And it was sufficient to enable chemists to develop the periodic table. Now let's move on. The nuclear notation. An atom is composed of a nucleus and electrons. The nucleus concept of nucleons, that is the protons and neutrons. A proton has a positive charge, a neutron, as its name suggests, has no charge. Outside the nucleus are the electrons. The charges on the protons and the charges on the electrons are known to have the same magnitude but with opposite sign of the electric charge. So the number of protons and electrons in an uncharged atom must be equal to a given overall neutral charge. Okay, so as a whole, atom is electrically neutral. Okay, now atom is electrically neutral and we have a positive component. So basically, it gives rise to a negative component. Now, Rutherford, according to his gold leaf experiment, was able to determine the existence of a center. Okay, exactly, a positively charged center. Okay, and that positively charged center is responsible for all the positive charge and all the mass that the atom has. Okay, now an hydrogen atom. A hydrogen atom, the simplest atom of all, consists of one electron and one proton. The proton is the nucleus of the atom. The electron is outside the nucleus. All atoms have a series of energy states determined by the probability wave that instantaneously describes the electron and therefore the atom as a whole. He is talking about quantum mechanics. Okay, in quantum mechanics, electrons do not behave as particles. They actually do behave as particles, but they also behave as waves. Okay, and it's not an actual wave. Okay, it's a mathematical calculation. Electron is not actually moving as a wave, but the modeling of the electron around the atom is considered to be that of a wave. We will discuss more about this in the later classes. Okay, the nucleus of every atom consists of an additional particle, the neutron, named for its charged neutral properties. The neutron is a form of nuclear packaging that allows protons to coexist with each other in a confined volume of the nucleus. Okay, now in the deeper understanding, you will understand more about why the neutrons actually exist. Okay, now a small theory that I'm going to give you is, you know that there is a positive charge, right? Protons are positively charged and protons are inside the nucleus, and inside the nucleus there is no gap. There is virtually no gap between the proton and neutron. Okay, so nucleus is basically one of the most densest materials on in the universe actually. Okay, a nucleus is a very dense material. There is virtually no gap between a proton and a neutron, or a neutron and a neutron. Now think about this. Two protons are positively charged. Okay, two protons are positively charged. Now we all know that there is a that as these two protons are positively charged, they would try to repel each other, right? The protons would actually try to repel each other. Now, when the protons actually start repelling each other, how do you think they are going to coexist? There exists another type of force known as a strong force. Okay. Now, this force, the nuclear force, we can call it a better name by the nuclear force. The nuclear force is stronger than the electrostatic force. So, there is an electrostatic force of repulsion that exists between two protons. Okay, that if if there is no force stronger than the electrostatic force, then the atom would not be able to form, right? Because there is only repulsion. Two protons, when they try to come closer to each other, then they will repel each other, right? So an atom as a whole would never exist because the nucleus can never be formed. Now think about this. Neutrons inside the nucleus act as buffers, okay, a small space between the two protons, so that there is a small decrease in the repulsion that exists between the two protons. Okay, similarly, they also give rise to the nuclear force. Okay, not the neutrons per se, but there is a nuclear force that exists between two subatomic particles. That nuclear force is able to overcome the electrostatic force of repulsion between the two protons and allow them to bind together uniformly. Okay, so neutrons act as padding or space so that they do not repel each other. Understood better?
Oh,
Okay,
yeah.
then okay, fine. If you have any doubts, please ask me now.
So basically, it will like once the neutron reduce the electrostatic forces which are repelled, and so it doesn't like affect the overall nucleus. So it keeps the nucleus stable. That.
Yeah, much that it's a simple definition. Okay, that is this is not the complete explanation though. We'll learn more about this, I hopefully later in the class. Okay. Now, the number of protons, electrons, and neutrons in a particular atom are important for the properties of nucleus. The term used are the proton number is called Z. It is also known as the atomic number. Okay, the number of protons that are present inside the nucleus of an atom also gives rise to the atomic number. This is the number of protons in a nucleus. It is unique to a chemical element that the atom represents. It is also the number of electrons in a neutral atom. Okay, now see, why do they say that? In a neutral atom, we know that both the proton and the electron have the same amount of charge, but with opposite polarities. Electron is negatively charged, whereas proton is positively charged. Okay, so the number of protons and the number of neutrons will always be the same in a neutral atom. Then and only then the overall positive and the overall negative charge can cancel each other out. Okay, so historically, the proton number was also called the atomic number. The proton number is also the number of chemical elements on the periodic table. That is how we arrange all the elements in the periodic table. Now, the modern periodic table given by Moseley, the definition of the periodic table is elements arranged according to a period. If when the elements are arranged, when the physical and chemical properties of elements are arranged in accordance with the periodic function of an atomic number, such a table is known as the modern periodic table. That means what? It means the whole of the periodic table is arranged in the ascending order of atomic number. For example, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon is all the elements having atomic number from 1 to 10. Then you have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium from 11 all the way to 20. Then you have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. That is 21 to 30. So all these elements in the periodic table, okay, I only know elements till 30. Otherwise, I know the elements in group size, like basically lithium, sodium, potassium, rubidium, cesium, francium. Then you have beryllium, magnesium, calcium, strontium, barium, radium. Like the downward ways also I know. Okay, but from 1 to 30 is what I know in the atomic number form. Okay, now the whole periodic table is determined by the atomic number. The positioning of the element in the periodic table is determined by the atomic number. Okay, now the atomic Is there only protons present inside the nucleus? No, there are protons as well as neutrons. Now the protons and the neutrons together are also referred to as the nucleons. Okay, anything that is available inside the nucleus is called a nucleon. Understood?
Oh,
Now, the nucleon number means what? How many nucleons are present inside the atom is called a nucleon number. Okay. Now, the nucleon number is also known as the atomic mass. Now, this is the type of number of protons plus the number of neutrons inside the nucleus. Historically, it was called the mass number or the atomic mass. Now, neutron number n. There is, yeah. So basically, you have the proton number or the atomic number. You have the nucleon number or the atomic mass or the mass number, and then finally you have the nucleon number, which represents the number of neutrons that are present inside the atom. And we all know that the atomic number Z plus the neutron number N will give you the nucleon number A. So number of neutrons is equal to atomic mass minus the atomic number. Clear?
clear.
Okay, algebraically, this is how it goes. Now, there is a shorthand to indicate the ingredients of a particular atom. Now, for example, you write the name of the element like this. Okay, you have, let's say, for example, carbon. Carbon's atomic number is 6. Carbon's atomic mass is 12. Okay, so at the bottom, you always write the atomic number, and at the top, you always write the mass number. Okay, clear? Now, if an element has for some reason some amount of charge present on top, then you can apply the number of electrons in the valence shell, or basically the charge that is gained by an electron by either losing an electron or gaining an electron can be represented here. For example, if sodium loses an electron, it becomes Na plus 1 electron, right? And that can be represented as sodium, whose atomic number is 11, whose mass number is 23, and whose charge is plus 1. Okay, so this is how you represent sodium plus. Clear?
Clear.
Okay, let's next. So this notation is used when writing nuclear equations later. The examples of this notation are: we have the helium He2,4, 2 protons, 2 neutrons, and 4 nucleons in total. Oxygen 816. Okay, 8 protons, 8 neutrons, and 16 nucleons in total. Oxygen 17. Now, oxygen 17 and oxygen 18. You must be thinking, what is this? Oxygen 17 and oxygen 18. Now, the only difference that exists between oxygen 17 and oxygen 18 is the number of neutrons. Okay, what are these elements known as? Oxygen 17 and oxygen 18? Isotopes, exactly. And what is the definition of an isotope?
Isotope is when an element has a same number of protons with different number of neutrons.
Okay. Now, tell me one thing, Akshay. Do isotopes have different physical and chemical properties?
Yes.
No. The isotopes usually have different physical properties because their weight is different. Okay.
Yeah.
But they do have similar chemical properties because the chemical properties of an element is it is determined by the number of electrons. Okay, the chemical properties of an element or an atom is determined by the number of electrons that are present in its valence shell. Okay, that's all that matters. Okay, so sodium is a reactive metal because it is able to lose 1 electron very easily. Chlorine is a very reactive metal because it is able to gain 1 electron very easily. That is why when these two, this cation, that is sodium ion, and this anion, when they come close to each other, they are able to form an electrostatic bond. They are able to form an electrostatic bond between the cation as well as the anion. Am I right?
Yes.
Okay. Now, here, so basically, isotopes have different physical properties because their mass is different. Because their mass is different, their volume will be different. Their atomic, their densities will also be different. Now, what are the 3 different isotopes of hydrogen? there is name for three different types of hydrogen. What are they?
Not
It's called protium. Say with me. Protium,
protein.
deuterium, and tritium. Okay.
Tritium.
Yes. For example, if oxygen actually combines with protium, you get the you get H2O. Okay. Deuterium, when it combines, you get D2O. Okay. And D2O is called heavy water. Okay. It's called heavy water, and it is used in a lot of nuclear reactors. Okay. Understood. It's called heavy water because it is heavier than normal water. Both of them contain hydrogen, but the hydrogen in water has only one proton in its nucleus, whereas a hydrogen in the heavy water basically contains a proton as well as a neutron. So every atom of hydrogen contains a proton and an extra neutron, making the overall water molecule heavier. The D2O molecule becomes heavier than the H2O molecule. Understood?
Yeah.
Okay.
Understood.
Now, next. State the number of protons and neutrons in the nucleus of uranium 235 92. Now, we know that number of protons is 92, right? What is the number of neutrons? 235 minus 92. Clear?
Yes.
Okay. Now, sodium 24. Now, this is also known as the isotope of sodium because sodium is the sodium's atomic mass is usually 23. So, you will have the number of protons will be 11, but the number of neutrons will be 13. Am I right?
Yes.
Okay. Okay. The Geiger, Martin, and Rutherford's experiment. In 1909, Ernest Rutherford from New Zealand was supervising the research of two students at a University of Manchester in England. One of these was a German researcher, Johannes Geiger. The other was an undergraduate, Ernest Martin. Now, they were studying the scattering. They were studying the scattering when alpha particles were incident on a thin gold foil in a vacuum. Now, a lot of questions should come in your head. First things first. What is an alpha particle? What is an alpha particle, Akshay?
Alpha particle is a two plus positive hydrogen basically.
No, not hydrogen, Akshay. No, 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 no. It's a
Okay. Helium.
helium. Okay. So basically, an alpha particle is He2 plus. Okay. It has two protons, two neutrons, and zero electrons. This is what a alpha particle is. Okay. Now, question number 2. Why use gold? Okay, why not use a cheap metal like aluminum? Did aluminum not exist back then? Of course, aluminum existed. Okay, but why choose gold instead of aluminum? Now, the reason behind this is that gold is a bigger atom. Okay, it is physically bigger as compared to aluminum. Okay, now because of the bigger atoms that are present in gold, they basically thought before they actually did this experiment, when they were designing this experiment, they basically had the J.J. Thomson's model in their head, right? Basically, they thought that if the atoms are big enough, then there will be small gaps. Just imagine bricks. Okay, just imagine a layer of bricks, a brick wall. Okay, so there will be small gaps between the brick walls. Similarly, they believe that the atoms, there will be small spaces between the atoms in the gold foil, and the electrons would act, the alpha particles being very small would actually pass through. A few of the alpha particles would pass through the gold foil, majority of them would actually bounce back. It's like throwing a ball on a ball with a couple of holes. Majority of the throws, the ball will actually come back. But sometimes, if you're lucky enough, the ball would actually go through the hole and pass through the ball. Right? That's what they actually thought. They thought that majority of the alpha particles would bounce back. Only a few would actually pass through the gold foil. And the reason for choosing a gold foil was that they wanted a big enough atom, for the alpha particles to actually bounce back, because aluminum compared to gold is a much smaller atom. So the number of alpha particles coming back would not be so significant. Okay, now this is actually where the whole thing changes. Okay, now when they actually do this experiment, they see that majority of the alpha particles, like 98 99% of the alpha particles, went straight through the gold foil as if there was no gold foil to begin with. Okay, they simply went straight through the gold foil. Okay, and that was a crazy thing, because for the first time in the whole of humanity, people finally realized that atoms are almost empty.
Explain.
Yeah, they're empty, they're completely empty. Okay, they're not completely empty, of course, they have the nucleus, but the size of the nucleus is very small. If I were to give you if I were to give you an example, think of the stadium, a football stadium. Okay, an oval or a circular shaped football stadium, and in that football stadium you have the small, what was the name of the fruit? Yeah, a small grape. One tiny grape is placed in the middle of the whole circular stadium. Then that circular stadium would represent the size of the atom, and the small grape in the center would represent the nucleus. Understood? Are you able to?
Understood.
Yeah. Some people,
In my
yeah, some people actually reduce the size even further. Have you ever seen a pepper seed? The seed of a pepper.
one?
Pepper seed, pepper, the black balls of
Yeah.
pepper seeds.
Yeah.
Yeah, some people call the nucleus to be even smaller than a grape, like that of a pepper seed, and the whole stadium is the size of the atom. So, as a whole, the atom is virtually empty. Okay, in 1909, so basically, what is happening? They were studying they were studying the scattering when alpha particles were incident on a very thin gold foil in vacuum. Figure 4 shows the basic experiment. When alpha particles collide with a fluorescent screen, light is emitted from the screen. A microscope detects these flashes of light. Geiger and Martson expected that the alpha particles to be deflected only through a small angle as a result of the electrostatic deflection by the diffused atom's charge, assumed that Thomson's model pudding was correct. So I'm still telling you that they actually believed that the Thomson's model was correct. Now, from the Rutherford scattering experiment, one thing that we can say with confidence is that Thomson's model is wrong. Okay, Rutherford suggested, however, that they should look at the same side of the foil as the alpha source. Okay, all three scientists were astonished to find that one alpha particle in 8,000 was reflected or scattered back by the thin gold foil back in the direction in which it came. So basically, 1 in 8,000, it basically came, hit, and came back. Okay, this could not have been a reflection from the diffused positive charge of the Thomson's plum pudding model, as the alpha particles were traveling too fast for that. So basically, see, even J.J. Thomson could have now said that, okay, you are bringing an alpha particle which is possibly charged next to, what do you say, an atom which has a negative charge in its nucleus, right? So sorry, a positive charge in its nucleus. So you could argue that the alpha particle is just being repelled by the positive charge, but they what they did was they increased the kinetic energy of the alpha particle to such a large extent that the electrostatic repulsion could be neglected.
Yeah.
See, we do this a lot of times when we are discussing about the subatomic particles. We most of the time we actually ignore gravity. Okay, we say that gravity has almost no influence on on the electrons, the protons, and the neutrons, because the electrostatic force of attraction is tremendous compared to that of the gravity. Okay, so so basically, they were astonished. Now, figure 5 shows the path of alpha particles coming in from the left. Two of these alpha particles have had head-on paths and they are deflected through angles close to 180 degrees. Other alpha particles have initial paths that lie further from the nucleus and so are deflected much less. So, majority of the alpha particles which were far away from the nucleus went straight through as if there was no gold leaf to begin with. Okay, some which were closer to the nucleus. Okay, the alpha particle is positively charged. Always remember that. Some that were closer to the nucleus, what happened when they became very close to the nucleus? What happened? The positive repulsion took place, and they were basically, what do you say, deflected by a small angle. Okay, now some were able to pass straight through as if there was no gold sheet to begin with. Some actually went near and they deflected backward by a small angle. Some went down. Some which were very close to the nucleus actually deviated even more. Okay, now you will be introduced to the properties of alpha particles in topic E3. For now, you need to know that alpha particle is a positively charged helium nucleus with He2 plus and 2 units of positive charge because it has lost both its electrons. Okay, it has lost both its electrons. Yeah. On reflecting on the results of the gold foil experiment, Rutherford later wrote that this was the most incredible event that has ever happened in my life. It was almost as incredible as if you fired a 15-inch shell from a large gun on a warship and a piece of tissue paper and it came back and hit you. I realized that this scattering backward must be a result of a single collision. And when I made calculations, I saw that it was impossible to get anything of that order of magnitude unless you took a system in which greater part of the mass of the atom was concentrated in a minute, he meant very small nucleus. So he came into two conclusions. One was the nucleus is positively charged because of deviations, the small deviations that you see in the electron. He resulted that the nucleus is positively charged. Now, looking at the bounce back that he saw by more than 180 degrees, he realized that almost entire mass of an atom has to be concentrated in a very small place inside the atom. And he called that very small place the nucleus. Okay, he called it the nucleus of an atom. Okay, it was then that I had an idea of an atom with a minute center carrying a charge. He also took inspiration from the solar system. Okay, for him, he believed that physics is showing us how a solar system actually works, how a galaxy actually works. A galaxy or a solar system has something that is a large mass at the center and tiny planets revolving around that large mass. Okay, so he also came to the same conclusion. He believed that the entire mass of the nucleus is concentrated in a very small section inside the atom, and he called that section the nucleus, and the electron was simply revolving around the atom. Okay, and like the planets revolve around the sun. Okay, now often scientific research requires patience and discipline. It is tempting to think that Geiger, Marx, and Rutherford's experiment was based on a single observation. Sorry. Certainly, Rutherford's response suggests a reaction to a single event. When Geiger published the data, he stated that over 100,000 scintillations were observed during the course of the measurement. Geiger and Martin had to sit in a darkened room and look for tiny flashes of light to record one scintillation. Now, what that means is basically, see, in the whole experiment, what was happening was the basically there is a gold foil here. Okay, in the center there is a gold foil, and this gold foil is covered by a small photolytic sheet. Okay, onto which when see, basically what is happening, the alpha particle is going like this and it is getting deflected and is basically hitting onto the wall of this container. Okay, just hold on 1 second. There should be an experiment, right? Oh yeah, I don't have to worry. There is. Look at this. See, here This is the what? This is the circular fluorescent screen. Now, I have already shown you what the effect of electrons striking on the fluorescent uh, powder looks like, right? The green glow.
Yeah.
So, similarly, these two scientists,
Until
yeah, so basically, these two scientists had to sit in a darkened room, okay, and they had to view the small flashes as the alpha particles struck the walls of the circular fluorescent screen, okay, and these small flashes were observed. They had to patiently observe this, okay, a long time. You can see they said 100,000 scintillations. That means 100,000 flashes of light were observed by these two scientists. Okay, now, so Geiger and Marsden had to sit. It's Marsden. Okay, had to sit in a darkened room and look for a tiny flash of light to record one scintillation. Okay, now it took about 30 minutes for their eyes to adjust to the dark and be sensitive enough to detect these flashes. Continuing the 100,000 flashes of light took weeks of effort. Okay, Rutherford wrote in a letter, Geiger is a demon at work of counting the scintillations and could count at intervals for the whole night. Retired after 2 minutes. Okay, retried after 2 minutes. It is unsurprising that Geiger developed a device for detecting radiation that is known as the Geiger counter. Okay, so basically a Geiger counter he was his job was in the gold leaf experiment to observe the particles that are striking the sheet, right? So basically
yeah.
he made a device which could detect radioactivity. Okay, radioactive decay basically leads to a large number of protons, neutrons, alpha particles being released when an atom actually decays. Okay, now these particles, when they decay, they throw out radiation into the environment. And if you have a Geiger counter in your hand, the Geiger counter can record these scintillations and it creates a beep. Okay, beep, beep, beep. If you are very close to, like, for say, a radioactive uranium material, okay, and if you bring this Geiger counter next to it, it will start beeping very fast because a large amount of radioactivity is actually taking place in uh, in and around that uranium atom. So basically, it will be like beep, 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 beep. So all that this is another basically a great invention that helped us in the advancement of radioactivity and radiology and all the other type of medical what do you say, medical instruments. Okay, now a Geiger Muller uh, counter. Okay, the alpha particles have a positive charge with magnitude twice that of an electron. Rutherford suggested that backscattering occurs because the atom consists of small, very dense, positive nucleus with electrons outside the nucleus. Okay, his calculations indicated that the diameter of the nucleus was about of the order of 10 to the power minus 15. We call that a femtometer. Okay, FM. Now, while the diameter of the entire atom was about 10 to the power minus 10. And 10 to the power minus 10 is also given a special name called the angstrom. Okay, so 10 to the power minus 15 is called a femtometer and is represented by FM, whereas 10 to the power minus 10 is called an angstrom and it is represented by A naught. Okay,
And
understood?
yes.
Okay, now the atom taken as a whole is almost entirely empty space. Okay, now figure 5 is not to scale because the nuclei spacing shown are drawn far too small. The nuclei in the diagram on the page are about 2 millimeters across. Nucleus at this scale should be separated by 2 into 10 raised to the power 5 millimeters, about 1/5 of a kilometer. Now, See, the nucleus right here, if this is the size of a nucleus, then the radius should be 500 meters. Okay, if this, can you see this in your book?
Yeah.
This small nucleus, if this is the size of the nucleus, then the radius has to be 10 to the power, sorry, it has to be 500 meters. So approximately much bigger than the football stadium. Okay, next. One fifth, oh sorry, 1/5 of a kilometer, 200 meters. So sorry, I read basically half. Okay, it's 200 meters. Now, the main results of this important experiment are that most alpha particles pass through the gold foil undetected or with very small deflections. So, about 90 to 99% of the alpha particles have no deflection to begin with. A very small alpha particles were deflected through a very small angle, but occasionally alpha particles rebounded in the opposite direction when they were in direct contact or when they were in head-on collision with the nucleus inside the atom. Okay, now what were the results that this experiment gave us? One thing, the most of the atom is a small dense region. Okay, the atom contains small dense regions of electric charge. The small dense region contains all the atoms positive charge. Okay, is that it? Is that it? What about the mass? You can also say that almost the entirety of all the mass of an atom lies inside the nucleus. Okay, so we know that the mass of a proton is 1.6 into 10 to the power minus 27 kgs, similar to that of a neutron, whereas the mass of an electron is 9.1 into 10 to the power minus 31 kg. It is about 10,000 times smaller than that of a neutron, okay, or a proton. So for all intents and purposes, we can neglect the mass of the mass of the we can neglect the mass of the electron. Okay, next. um yeah, okay, should we, do we have to an analogous of the alpha particle scattering? Inquiry 1 demonstrates creativity. I don't think we have to go through this, right? Let's actually go through. No, we'll actually go through this. Okay, let's see. Hmm, okay, so demonstrative creativity in the designing, implementation, or presentation of the investigation. Inquiry 1. Develop, investigate. Okay, wait. Alpha particle scattering experiment can be uh, simulated using a specially shaped hill and a ramp. The hill is made so that its height h above the surrounding is inversely proportional to the distance r from the center of the hill. This means that if this means that it simulates simulates using gravity the electric potential due to the positively charged nucleus. Okay, now the apparatus itself, h is inversely proportional to r, the shape of the hill. Okay, what else do we know? Metal sphere ball bearings are rolled down the ramp. They are rolled down the ramp. Okay, fine. The starting height of the sphere determines the sphere's speed as it leaves the ramp. Basically, we know that if you have, it's like a Hot Wheels car, right? You have a ramp and you have a Hot Wheels car. The speed of the car is basically determined by the height of the ramp. The higher the ramp, the higher the potential energy, and the potential energy gets eventually converted into kinetic energy as the car rolls down the ramp. Okay, the starting height of the sphere the starting height of the sphere determines the sphere's speed as it leaves the ramp and therefore its kinetic energy. Design an experiment that either varies the initial energy of the sphere or the distance between the initial direction of the sphere and the center of the hill. This is called the offset. The meaning of the offset is shown in plain view in figure 9. Okay, in figure, where is figure 9? Yeah, so this is the offset angle. I don't think this is particularly that important. Okay, you can use, okay, so basically what is happening here, a ball is coming down like this. Okay, look at this diagram. Okay, a ball is rolling like this. Okay, now when the ball comes here, if it has enough energy, what will happen? It will move straight through and go inside this hole. But most of the balls, they're not going to follow this path. They are not going to follow this path. What they will do is they will fall, and then they will basically move up the ramp slightly, but since their direction is not the same, they would simply go here, and then they will somehow roll off this basically this shell. This is what's happening here. Look at this. So it came,
Yeah.
but it was not at the center. The particle, the electron, was not in the central path. So what did it do? It basically deviated from the center and moved somewhere else. Okay, this could be considered, this could be construed as the deviation that the alpha particles actually face when they are near the nucleus. So when they're near the nucleus, if they are not actually in a head-on collision with the nucleus, what they will do, they will simply get deviated by the electrostatic repulsion. Okay, you can use the apparatus uh, qualitatively to find out how different initial kinetic energies of different offsets affect the deflection angle. Or you could devise a quantitative experiment to check the elements of Rutherford's equation. The equation from the data based question, n is inversely proportional to the fourth power of sine of phi by 2, where phi represents the angle of deviation, is a good place to start. You might then investigate how the number of scatterings at a particular angle vary with the initial kinetic energy. Think carefully about the statistics of the experiment and how you would treat the experimental errors. Okay, so this is something that you have to do on your own, and I think your school will make you do this experiment. Okay, now, so 1 second. So students, I am going to end this class today here, and we will continue with the next section of the chapter in tomorrow's class. Okay, I really hope you like my videos, and the explanations that I'm giving you is quite okay. And if you like my videos, please do like, share, and subscribe. And I'll see you in the next class. Thank you so much.